Hi everyone, welcome to the first webinar of a series of 3 different webinars on contamination. The first webinar, the one of today, will be on Hydrogeology 101, so just the basic notions of hydrogeology. The second webinar will be on environmental site assessment studies, and the third one will be on environmental sampling, analysis, and interpretation. So today's webinar is organized by the First Nation of Quebec and Labrador Development Institute. And here we go. So why should you take this training course? So why should you follow this webinar? First is to have a better understanding of environmental study reports. It's also to have a better understanding of the work of hydrogeological and environmental consultants that maybe a band council can hire. It's also maybe just to improve your knowledge of hydrogeology. And it's to understand and give you all the basic notions of hydrogeology that will help you understand the contaminant behavior in the environment, mostly in soil and groundwater. So it's going to help you for the following webinars as well. The webinar is going to be divided into 5 different chapters or 5 different sections. The first one is what is hydrogeology. The second one is what is its utility. The third one is FlowContamination Principles. The fourth one, characteristics of contaminants that affect their spread in the ground. And we're gonna go finally with soil characteristics that affect the spread of contaminants. What is hydrogeology? So the first section, first chapter. Hydrogeology is the science of studying the relationships between groundwater and geological materials and processes. It concerns groundwater quality studies, wet installations, the preservation of the quality of exploited groundwater, or the decontamination of groundwater. So now for the second chapter, what is its utility? What is the utility of hydrology? Hydrological studies support work related to the exploitation of underground resources. Hydrologists determine the location of the wells, the design of the facilities, the drilling methods used, what equipment to use, and the materials that will be needed. It also enables the quality of groundwater to be monitored. This is particularly relevant in project studies such as urban, industrial, mining, agricultural, or civil engineering projects where potentially negative effects on groundwater have been determined. It will also be very useful in any environmental site assessment study that we will talk about in the second webinar. And finally, when there is a case of groundwater contamination, a hydrologist will put in place a decontamination plan and also ensure its implementation. Now the third chapter is on FlowContamination Principles. I will now talk about the principles governing the flow of water and contamination through soil. The following picture is a diagram of the water cycle on the Earth. Water evaporates from water points such as oceans, rivers, and lakes. It rises into the atmosphere where it condenses and then falls back to Earth in the form of rain or snow. Once the water reaches the ground, it will run off and slowly seep into the soil until it reaches the groundwater, also known as the aquifer. An aquifer is a porous medium made up of geological materials that allows the capture of a sufficient quantity of groundwater. Once water reaches the water table, it will continue to flow to an emergence point such as a water source, lake, river, or ocean. The water is back to its starting point and the cycle begins again. Soil contamination can be produced by a variety of pollutants. There are a great many of them and they can be classified into several different categories. There are organic and inorganic contaminants. Organic contaminants are microorganisms such as bacteria and viruses, dead organic matter such as manure, hydrocarbons such as petroleum and its derivatives, or persistent organic pollutants called POPs, such as solvents, pesticide, insecticide, and fertilizers. Organic contaminants are often found on agricultural land. When the farmland is extensive, the soil becomes saturated and the excess water starts to flow when it rains, contaminating the surrounding waters. They are generally toxic to the fauna and flora of the soil. They are generally toxic to the fauna and the flora of the soil. In addition, they can cause acceleration or eutrophication of water bodies. Eutrophication is the excessive buildup of nutrients in the water, which causes a dense growth of plant life. In other words, it accelerates the process whereby a lake becomes a swamp. Next, there are the inorganic contaminants. Inorganic pollutants are mainly in the form of heavy metals such as lead and mercury. They can be found in landfills, domestic and industrial waste, or in oil extraction sites and in atmospheric pollution. Their presence in large quantities in the soil is very harmful for the environment. They result in damage to soil fertility and contamination of rivers and groundwater. Then, they are in liquid, gaseous, or metallic form. Liquid contaminants are simply contaminants that are in liquid form such as gasoline or solvents. Gaseous contaminants are in the atmosphere. One of the best known is sulfur dioxide, which comes from industries and fossil fuel combustion. Metallic contamination is due to metals such as aluminum, arsenic, chromium, cobalt, etc. It can also be due to heavy metals like mercury, cadmium, lead, etc. These metal contaminants come from many sources. They can come from plant discharges such as from paper mills, the spreading of certain products in agriculture, the use of certain fungicides, the fallout of atmospheric particles emitted during the combustion of automobile gasoline, the incineration of waste, the leaching of rocks in mine and rainwater runoff from roads and roofs. Next, there are contaminants that are described as miscible and immiscible. A miscible pollutant is a pollutant that can be mixed with water and create a homogeneous solution. A good example is the de-icing salt that is used during the winter to de-ice roads. Immiscible contaminants are substances that are unable to mix with water. The solution will remain heterogeneous. Heavy metals and certain hydrocarbons such as oil and gasoline are good examples. In addition, since these contaminants are unable to mix with water, they will accumulate on the surface or bottom of the aquifer according to their weight relative to that of the water. There are also the pesticides, herbicides used against organisms that are considered undesirable. Finally, there are the pharmaceutical contaminants. They come from wastewater containing excreta from people or patients who have absorbed them, from the uncontrolled elimination of pharmaceutical products, for example when drugs are thrown into the toilet, and finally from runoff water containing animal waste from animals that have received veterinary treatments. Contamination is not necessarily caused by a direct discharge of harmful substances to the soil, depending on the form in which contaminants are found. In some cases, it is transported by the rain. For example, if a solid soluble contaminant is spilled, it will not seep into the soil until it has an access to a solvent. So, when it rains, the contaminant will dissolve in the water and continue on its way through the soil. In some cases, contaminants can come directly from the rain. Contamination of soil and groundwater can come from many sources of contamination such as urban sites such as sewers and gas stations, industrial sites such as landfills and mines, agricultural land, and finally urban infrastructure such as septic tanks and sewers. Pollutant pathway in the soil. We will now take a look at the typical flow path of a contaminant in the ground. First, there is a spill of a polluting substance here represented on the image by number 1. Once the pollutant comes in contact with the ground, it will flow vertically through the unsaturated zone until reaching the surface of the groundwater table. The unsaturated zone is the area of the soil where the pores are not completely filled with water, unlike the groundwater where the pores are completely filled with water. In addition, depending on the nature of the pollutant, part of it may be degraded by microorganisms in the soil or be absorbed by plants. Once it reaches the water table, it will continue flowing along a subhorizontal path according to the direction of groundwater flow as shown in number 3 of the image. It is at this point that the contaminant plume begins to form. The contaminant plume is the boundary that delineates where the pollutant extends into the environment. The closer you are to the source of contamination, the higher concentration is. So the more the plume expands, the lower the concentration will be at its perimeter. It is important to remember that we must intervene as quickly as possible to stop the source of contamination. The following image represents an example of the propagation of a contamination plume according to the number of days passed. Example, you have 2,000 days, 4,000 days, 6,000 days, and 8,000 days. So looking at the image, we can see that the more time passes, the more the plume grows in size. If the contaminant spill is stopped at its source, the plume will continue to expand according to the current of the water. However, its concentration will be much lower. There are many characteristics that can be influenced the course of pollution plume as well as the shape that it will take, and we'll explore them in the next two sections. Chapter 4. Characteristic of contaminants that affect their spread in the ground. The physical and chemical properties of a contaminant can modify the behavior of a pollution plume, such as its speed of propagation and its shape. Now we're going to see some examples as some different physical and chemical properties. So the first property that we will talk about is volatility. Volatility is the ability of a substance to evaporate. So the higher the volatility of a spilled contaminant, the more it will tend to evaporate before infiltrating the soil. So there will be a smaller amount of contaminants that will be able to seep into the ground and go into the groundwater. Gasoline is a good example of a volatile substance, and for instance, fuel oil and PCBs are examples of non-volatile substances. Now the second characteristic that we'll talk about is solubility, which is the ability of a substance to dissolve in water. When a soluble contaminant mixes with water, it will flow at the same rate as water in the soil, while the pollutant that is insoluble will continue to flow at its own speed, even if there is a water supply. It will not mix with water. In addition, when a highly soluble contaminant comes into contact with the groundwater, it will dissolve in the aquifer and contaminate a large part of the aquifer, while an insoluble contaminant stays on top of the water table or extends below the water table. It will not mix with water. Then, a third characteristic is the viscosity, which is the resistance of a fluid to its flow. So the higher the viscosity is of a contaminant, the more slowly it will move in the soil. The contamination will be much slower. So the fourth and final characteristic that we will talk about is density. Density is the ability to float or sink. In the case of a contaminant that is denser than water, it will cross the saturated zone vertically and go directly to the base of the aquifer. As can be seen in the image on the left, this causes contaminant accumulation over the entire left between the soil surface and the bottom of the aquifer, which in turn causes a much larger pollution plume. Whereas when the contaminant is less dense than water, for example gasoline, it will flow vertically, but its course will stop at the surface of the groundwater. The image on the right shows that the concentration is much lower than in the case of contamination with a more dense contaminant, such as chlorinated solvents used for dry cleaning. So we've been talking about the characteristic of the contaminant. Now we will talk about the different characteristic of the soil that can affect the spread of contamination. We've been talking about the different characteristic of the contaminant. Now we will talk about the characteristic of the soil. The first one we'll talk about is the type of permeability. Permeability is the property of a rock, of the ground, or of a body to allow water to penetrate. There are two types of permeability: interstitial permeability and fracture permeability. In a medium with interstitial permeability, typical velocities can range from a few centimeters to a few hundred meters per year. For example, water and sand can spread up to 920 meters a year, while in a fracture environment, when the fractures are well interconnected as in the image on the right, the flow velocity can be very high, up to a few hundred meters per year. However, it is rare that in nature the fractures are well interconnected. Often the fractures do not meet, so the contaminant will settle in the fractures, but cannot go further into the ground. In conclusion, Contamination in media with interstitial permeability is usually faster than in a fracture medium, since it is almost always connected with the groundwater table. The permeability of interstices is measured according to the pore size. Many parameters can affect the porosity, permeability, and speed of movement of contaminants. First, the finer the sediment, the greater the contact area between water and sediment. This will increase the frictional force between water and solids, thereby reducing the flow rate. For example, between gravel and sand, the water will flow less quickly in the sand than in the gravel. Then, the permeability increases with the average size of the particles, since the pore size increases. Looking at the first two images on the left of this slide, it is easy to see that the pores between the coarse grains represent a larger area than those of the fine grains. The spread of contaminant is therefore faster when the grains are coarse. The more the standard deviation of the grain diameters increases, the more the sample becomes heterogeneous, so that the fine materials can fill the voids between the coarser fragments, as can be seen in the third image. The permeability is therefore reduced. When comparing rounded grain soils and angular and irregular grain soils, it is possible to observe that rounded grain soils compact much better and have many fewer pores compared to the irregular and angular grain soils. In other words, contaminants will flow much faster through gravel soil than in beach sand. Over the next few slides, I will talk about the nature of the soil, as it can also affect the propagation of pollutants in soils. So in sandy soils that are mainly composed of sand, the porosity is very high. In such a soil, the contaminants will flow and expand much faster given the high porosity. Silty soil consists of silts whose particles are relatively tightly packed, allowing the liquid to move more or less easily. The silt is rock or fine particles carried by water and deposited on the beds and banks of rivers. It looks like clay but a little coarser. The path of contaminants is slowed by the type of soil. In addition, when silty soils are subject to drought conditions, a very hard crust is formed on top, which creates a barrier that prevents water from infiltrating to a certain extent. Humiferous soils consist mainly of organic matter where water flows easily. In this type of soil, the spread of pollutants is relatively fast given the high porosity. Humiferous soils are mainly found in agricultural areas. They are used mainly for their high fertility and their high drainage capacity. Then, there are clay soils composed mainly of clay. They have a very low porosity and leave little room for the circulation of liquids. The capacity of the pollutant to spread in such a soil type is therefore very small. This is why they are used as impervious layer in various situations and when creating catch basins. And then there are natural barriers that are made of clay and silt. As previously mentioned, these are types of soils that have low porosity and are relatively impermeable. So when a natural barrier is present, it can prevent contamination from continuing on its way to the groundwater. Finally, I will tell you about the types of rock. First, there are sedimentary rocks. Sedimentary rocks are created by the compaction of sediments in the bottom of a body of water, such as an ocean. They are relatively friable rocks, usually composed of horizontal layers. They are located mainly in southern Quebec and along the St. Lawrence River. A good example of a medium composed of sedimentary rock is Anticosti Island. They are rocks whose porosity is relatively high but variable. So in some cases, if it undergoes mineral dissolution, there will be a much larger quantity of pores. The contamination will therefore be faster in this type of soil. Platonic and metamorphic rocks are very hard rocks with very low porosity. These are rocks that mostly have fracture porosity. There is practically no empty space between the crystals, and in the absence of fracturing or alteration, the porosity is zero. Unless severely fractured, these are environments where the possibilities of contamination are very low. Plutonic rocks are mainly present in northern Quebec, and metamorphic rocks cover a large area along the St. Lawrence River, found in both Abitibi and the North Shore. So finally, the sixth and final chapter is just a reminder of the important points to remember. The more time passes, the more the pollution plume will grow. It is really important to intervene as quickly as possible by stopping the flow of contaminant at its source. Then, the finer the sediment, the slower the flow velocity. So if the contamination occurs in a medium such as a gravel soil, compared to a sandy soil, the contamination will be faster in the gravel soil. The larger the standard deviation of the grain diameters, the lower the permeability will be. So a heterogeneous soil will be much more impermeable than a homogeneous soil. Sandy soils are very porous and do not hold water. The flow velocity is very high. Silty soils are places that allow more or less passage for fluids, or callus. And last 2 points to remember is that sedimentary rocks are suitable environments for contamination because of their sometimes high porosity, depending on the case. And finally, the plutonic and metamorphic rocks that are not fractured or altered have zero porosity, so the risk of contamination in this type of soil is very low. So this is it for today's webinar. If you have any question on the webinar, if something is not clear enough, please feel free to send us an email or call us at the FNQLSDI. We'll be very pleased to answer if we can. If we can't, we will send your question to the right person that will be able to answer your question. Also, this webinar was made possible thanks to the financial contribution of Indigenous Services Canada, so thank you. And finally, you know that there are 2 webinars that will follow this one. They will be available online on our website, so go have a look at our website and you should be able to find the other webinars. Thank you and have a nice day.